So we have as x approaches to pi by 4, h approaches to 0. Now from first and second, limit h approaches to 0 under root 2 cos of x is pi by 4 plus h minus 1 upon, this is cot of pi by 4 plus h minus 1. So this can be written as limit h approaches to 0, it is under root 2 cos a cos b minus sin a sin b. Now minus 1 upon, what is that? It is cot a cot b minus 1 upon cot b plus cot a minus 1. So if we further simplify this, you can see here it is, this is your cos h minus sin h minus 1 upon cot h minus 1 upon cot h plus 1 minus 1. So this can be written as limit h approaches to 0. This is cos h minus sin h minus 1 upon cot h minus 1 minus cot h minus 1 into, what is that? It is cot h plus 1. So this will cancel. Now this can be written as, this is limit h approaches to 0, 1 minus cos h plus sin h upon h into, what is that? It is 1 plus tan h upon h. You can see here as h approaches to 0, this is 1 minus 1 is 0, 0 upon 0 into, so again it is 0 upon 0 form, that is your still it is undefined form. To simplify this, can I write this as limit h approaches to 0, 1 minus cos h is 2 sin square h by 2 plus 2 sin h by 2 into cos of h by 2 upon h into 1 plus tan h upon h. Okay, now so further this can be written as, this is your limit h approaches to 0, 2 sin h by 2 into sin of h by 2 plus cos h by 2 into 1 plus tan h upon tan h upon h. I am sorry, because of the space I am going to write here, so it is should be in this block. So what is that? It is limit h approaches to 0, 2 sin h by 2 upon h by 2 into 2 into limit, what is that? It is h approaches to 0, this is your sin h by 2 plus cos h by 2. So there is something wrong here, it is, there is no h here, I am sorry, I am going to solve this question. So because it has been mistake here, it is, this is your cos, limit h approaches to 0, cos h or 1 minus cos h plus sin h upon, so this is the, here is the mistake here. So let me solve this question from this step onward. It will be limit h approaches to 0. What is that? It is 1 minus cos h plus sin h upon, it is 2 times into 1 plus tan h upon tan h. What is that? It is limit h approaches to 0, 2 sin square h by 2 plus 2 sin h by 2 into cos of h by 2 upon 2 into limit h approaches to 0, this is 1 plus tan h upon tan of h. So by mistake I had written h here, which is wrong. It is, that is minus 2, taking a negative common from the numerator and denominator, it is positive 2 here. So at this place it is limit h approaches to 0. If I take 2 sin h by 2 common, it is sine of h by 2 plus cos of h by 2 upon 2 into limit h approaches to 0 1 plus tan h upon tan h. Now upon h into h, so from here upon h by 2 into 2. So again, say, let me write down this step here. So this is your 2 sine h by 2 into sine h by 2 plus cos h by 2 upon, this is your 2 here. Now this will cancel. So this is equal to limit h approaches to 0 sine h by 2 upon h by 2 into 2 into h into limit h approaches to 0. What is that? It is sine h by 2 plus cos of h by 2 into limit h approaches to 0. What is that? It is 1 plus tan h upon tan h upon h into h. Now you can see here this and h and this h will cancel. So this limit is equal to 1. So this is equal to half into 1 into this limit is 1 into 1, which is equal to half, because limit h approaches to 0 sine h by 2 upon h by 2 is equal to 1, and limit h approaches to 0, that is your tan h over h, that is also equal to 1. So I'm sorry, because of the constraint in the space, so this is equal to, that is half here. So this way we have been able to find out the value of the function at pi by 4, which will make this function continuous at x is equal to pi by 4. Now next is show that fx is equal to, it is sine 3x upon tan 2x for x less than 0, and this is 3 by 2 for x is equal to 0, and log of 1 plus 3x upon e raised to power 2x minus 1 for x is greater than 0 is continuous at x is equal to 0. So continuity at x is equal to 0 means that we will find the left hand limit, right hand limit, and the value of the function at 0 is given. So first of all, let me find the left hand limit, which is your limit x approaches to 0 negative sine 3x upon tan 2x. So this is limit x approaches to 0 negative, it is sine 3x upon 3x into 3x upon tan 2x upon 2x into 2x. You can see that this factor will cancel. This is equal to, that is your limit x approaches to 0 negative sine 3x upon 3x upon limit x approaches to 0 negative tan 2x upon 2x into 3 by 2, which is equal to 1 into 3 by 2. This is equal to 3 by 2. So the left limit is 3 by 2. What is the right hand limit? It is limit x approaches to 0 positive. It is log of 1 plus 3x upon e raised to power 2x minus 1. So you divide by 2x, correspondingly multiply by 2x. Why? Because limit x approaches to 0, e raised to power x minus 1 over x is always equal to 1. Now because limit x approaches to 0, log of 1 plus x upon x is equal to 1. So this is equal to limit x approaches to 0 positive, log of 1 plus 3x upon 3x into 3x upon e raised to power 2x minus 1 over 2x into 2x. Now this will cancel. This is equal to 1 into 3 by 2 into 1 over 1, which is equal to 3 by 2. So we can see here from first and second. So from first and second, left hand limit is equal to the right hand limit is equal to 3 by 2, which is the value of the function at x is equal to 0, which clearly shows that this function is continuous at x is equal to 0. Now next is continuity in the interval. Next is continuity in the open interval AB. A function fx is said to be continuous in the open interval AB if it is continuous at all the points within the interval AB. Continuity in the interval implies continuous at all the points in the open interval AB, and continuity in the closed interval AB implies continuous at all the points in the open interval AB, and limit x approaches to a positive fx is equal to f of a, and limit x approaches to b negative fx is equal to f of b. So what do you mean by that? That means function should be continuous everywhere in the open interval AB. It should be right continuous at a because you cannot go to the left of a, and it should be left continuous at b because you cannot go to the right of b. So that will make the function continuous in the closed interval AB. Now, for example, question is show that fx is equal to modulus of x minus 4 over x minus 4 for x not equal to 4 and is equal to 0 for x is equal to 4 is everywhere continuous at x is equal to 4. So that is, we have to show that this function is everywhere or okay, you can say that we have to discuss the continuity of fx over R. Now let's say the statement is discuss the continuity of this function over whole of the real line. Now you can see here this is equal to 1 when x is greater than 4, it is minus 1 when x is less than 4, and is equal to 0 when x is equal to 4. So limit left hand limit is equal to limit x approaches to 4 negative fx, this is equal to minus 1. Right hand limit is this is equal to limit x approaches to 4 positive fx, this is equal to 1, which clearly shows that this is discontinuous at x is equal to 4. Now, but for all the points of x greater than 4, fx is equal to 1 being constant is continuous everywhere. Similarly, for all the points of x less than 4, fx is equal to minus 1 being constant is continuous everywhere. So which shows that this function is continuous everywhere except at x is equal to 4. Question was to discuss the continuity of the function over whole of the real line. Now convincingly we can say that this function is continuous everywhere except at x is equal to 4. Now next is show that fx is equal to modulus of 1 minus x plus mod of x and its mod is everywhere continuous. We have to show that this function is everywhere continuous. Now this is equal to 1 minus x plus x modulus if x is greater than or equal to 0. This is 1 minus x modulus if x is less than 0. So which means that this is equal to 1 if x is greater than or equal to 0. It is modulus of 1 minus 2x if x is less than 0. Now we will define this function once again. So this is equal to 1 if x is greater than or equal to 0 is 1 minus 2x if 1 minus 2x is greater than or equal to 0 and x is less than 0, and is 2x minus 1 if 1 minus 2x is less than 0 and x is less than 0. So you can see here this is 1 if x is greater than or equal to 0 and is 1 minus 2x if 1 is greater than or equal to 2x means x is less than or equal to half and x is less than 0, and is 2x minus 1 if x is greater than half and x is less than 0. Now the value of x is greater than half and less than 0, so that means their intersection is 5. So only possibility is 1 if x is greater than or equal to 0. It is 1 minus 2x if x is less than 0. Now we have a function defined which is called piecewise function. Now we can check the continuity of the function here. So first at 0. Now at x is equal to 0, left hand limit is equal to limit x approaches to 0 negative, that is your 1 minus 2x is equal to 1. Right hand limit is equal to limit x approaches to 0 positive 1 is equal to 1. F of 0 that is also equals to 1. So from first, second and third you can see that this function is continuous and x is equal to 0. But now the question is we have to prove that this function is continuous everywhere. For all x greater than or equal to 0, fx is equal to 1 is a constant function and hence is continuous in its domain. So this should be the argument here. Now for all x less than 0, 1 minus 2x is a linear polynomial and hence is continuous in its domain, implies fx is continuous everywhere. So I have been able to prove that this function is continuous everywhere, but once again let's discuss this point. Every polynomial is continuous over all of the real line, or you can say every polynomial is continuous in its domain, whether it is your linear polynomial, quadratic polynomial, cubic polynomial, multinomial, it is everywhere continuous in its domain. So straightway you have to write on the argument that why it is continuous everywhere. You have to give the reasons for that. So the reason is that this being a linear polynomial is continuous in its domain, which is your x is less than 0. For greater than 0, constant function is continuous. At x is equal to 0, we have been able to prove that this function is continuous. Now next is for example, next question is fx is equal to 1 over x minus 1. So find the points of discontinuity of f of x. So let us discuss the points of discontinuity of f of fx. Now if a function is not defined at a point, so how can it be continuous at a point? Since 1 over x minus 1 is not defined at x is equal to 1, so therefore x is equal to 1 is the point of discontinuity of fx. Now come to f of x. When we have to find f of x, can I say that it is 1 over fx minus 1? So 1 over fx minus 1 means that it is 1 over x minus 1 minus 1. So can I write this as 1 over 1 minus x plus 1 upon x minus 1, or it is x minus 1 over 2 minus x. Now 2 minus x should not be equal to 0, that is x should not be equal to 2. So therefore points of discontinuity of f of x are, they are 1 and 2. So 1 and 2 are the points of discontinuity of f of x. Now next is prove that greatest integer function is continuous everywhere except at integers. Now before discussing this, let me plot the graph of the greatest integer function. This is 0 to 1, 1 to 2, 2 to 3, 3 to 4, then you have minus 1 to 0, minus 2 to minus 1, and so on. So between the interval 0 to 1, this is 0, 1 to 2 it is 1, 2 to 3 it is 2, 3 to 4 it is 3, minus 1 to 0, minus 1, minus 2 to minus 1, minus 2, and so on. So let us discuss the continuity at x is equal to 1. You can see here limit x approaches to 1 negative integral part of x, this is equal to 0. From the graph it is clearly visible that when x is less than 1 it is 0 here. Limit x approaches to 1 positive integral part of x, this is equal to 1. 1 positive, the value lies in the interval 1 to 2, which is your 1 here. Now what is f of 1? So that is also equals to 1. Since these three are not same, so which clearly shows that this is discontinuous at x is equal to 1. Implies that it is discontinuous at every integer here. Now let us consider any point. Let's say consider any point a belonging to the interval 1 to 2. In this interval you can see that limit x approaches to a negative integral part of x, that is also 1 because it belongs to the interval 1 to 2. Limit x approaches to a positive integral part of x, that will also be equals to 1, and f of a, that will also be equals to 1. So similarly, whenever the point lies within the interval, open intervals, in the continuous interval, whether it is 0 to 1, 1 to 2, 2 to 3, and so on, similarly on the negative side, it is always going to be continuous, but at the integers this function you can see here is always discontinuous here. Even by considering any particular integer, say k, that is, let us consider any integer k. We have limit x approaches to k negative integral part of x, this is equal to k minus 1, and limit x approaches to k positive integral part of x, this is k, and f of k, that is also equals to k. So from first, second and third, they are all not equal, so therefore this function is discontinuous at the integer k here. further certain questions based on the continuity. Let us say fx is equal to cos square x minus sin square x minus 1 upon under root of x square plus 1 minus 1 when x is not equal to 0 and is k when x is equal to 0. So question is, this function is continuous at x is equal to 0, so find k. So once again, when this function is continuous at x is equal to 0, that means its limit exists. So therefore limit x approaches to 0, cos square x minus sin square x minus 1 upon under root of x square plus 1 minus 1, this must be equal to f of 0, which is your k. Or limit x approaches to 0, cos 2x minus 1 upon under root of x square plus 1 minus 1, this must be equal to k. So can I write down the numerator as minus 2 sin square x? Now rationalize the denominator into under root of x square plus 1 upon under root of x square plus 1 plus 1. This must be equal to k. So minus 2 times limit x approaches to 0. This is sin square x upon x square plus 1 minus 1 into limit x approaches to 0 under root of x square plus 1 plus 1. This must be equal to k. Now this limit is equal to 1. This is minus 2 into 2 is equal to 4. So which is equal to minus 4 here. This way we have been able to solve the questions relating to, that is your continuity.